Okay, good morning, everybody. Today we're talking about Maxwell relations. They're in Atkins 3E. Maxwell relations are named after this guy, James Clerk Maxwell, one of your all-time great scientists. Most famous for Maxwell's equations used to describe electricity and magnetism, but also made some important contributions to thermodynamics. So I'm going to divide this up into two parts. There's two. The first part, the first video is going to be a review, a crash course in multivariable calculus. It's not comprehensive. I'm focusing on the parts which will be particularly useful to understand Maxwell relationships. If you need some more background, they're described here in the Chemist's Toolkit. Right? So Chemist Toolkit 9 and 10, which are in these sections of the text. All right. Real quick, in one dimension, we have a derivative, which we write df dx, right? We associate the derivative with the slope at some point. In two dimensions, I now have a function f, which is a function of the variables x and y. And we talk now about a partial derivative. This symbol here means partial derivative. The meaning of it is the same. It is a slope. But the caveat is that we now have to consider it at some specific y value. So we talk about the slope with respect to x at a constant y. In one or two dimensions, we can talk about a differential. The differential describes the change in the function if the variables are changed by some small amount. So in one dimension, the differential df is simply df dx times dx. It's the slope, I'll do it with my pen, the slope times the run. Right? That's the change in f. In two dimensions, this is the expression for the total differential. Right? It's the slope with respect to y. Sorry, I said y, but this is the slope with respect to x times the change in x, plus the slope with respect to y times the change in y. The meaning here is the exact same. It will describe the total change in the function in terms of these two slopes. And what you need to know is that I can write this expression, the total differential of a two-dimensional function, by definition. Right? That is, if I tell you that f is a function of the variables x and y, you can write this. And I'll work through this example for you, although if you want to try it on your own, just pause the video here and see if you can do this. Imagine now I have some function p, which is a function of the variables v and t. Write the total differential. You want to try it on your own, pause for a second. If you just want to see how to do this, you can follow me. All right, in order to do this, all you do is follow this formalism. dp, the change in p, equals the slope with respect to one variable. So I'm going to do v first. It's the change in p with respect to v at constant t times dv. So this is the slope with respect to v times the change in v plus the slope with respect to temperature when volume is constant times dt. I can write that by definition for any function I want. All right, these expressions, differentials, have two major uses. We can use the differentials to define any partial derivative we want. And I'm not going to go into great detail here. I'll give you some more notes on this in Canvas, which will describe how you do this. You can also look in Atkins. He has some stuff there. But the more important one here is the second. We can use differentials to learn about the function itself. And number two here is particularly useful because in thermodynamics, we often can't directly define a function. I don't know what the function is, but I do know how it changes. And so that becomes useful. So let me dig into this a little bit. There are a class of functions which are called exact functions. Exact is a mathematical term. And here's how you think about that. Imagine some total differential, which is written as follows. df equals g of x and y times dx plus h of x and y dy. This is written a little bit differently, but g of x and y and h of x and y are just some arbitrary functions of x and y, right? They could be derivatives, they can be constants, they're just some arbitrary function. Exact functions are ones for which the derivative of g with respect to y is equal to the derivative of h with respect to x. Or equivalently, if I recognize that this function g is the change in f with respect to x, right? That's here. This is the change in f with respect to y, that's here. I can write the expression as follows. And this makes it a little clearer as to what's important about these exact functions. In exact functions, you're evaluating a type of second derivative. You can see that they look like second derivatives. But what's different about them is the order of operations. We start from the inside out. So on the left-hand side, we're first going to take a derivative with respect to y, and then a derivative with respect to x. On the right-hand side, we're first going to take a derivative with respect to x, and then y. Right? So exact functions are ones for which this is true. And I'm going to give you one example here. F equals 2xy squared. Is this function exact? If you want to follow along, you can follow along. If you want to try this yourself, you can try it yourself. Here's how this goes. What I first need to do is evaluate one of these partial derivatives. So I can pick either one. I'm going to take the partial of f with respect to x when y is held constant. If y is a constant and I take the derivative of this with respect to x, you get 2y squared. The other one I'm going to evaluate is the complement to this. So that is the partial of f with respect to y when x is held constant. If I take this with respect to y, the derivative with respect to y, I am going to get 4xy. These two are not equal. But remember, in order to evaluate whether or not a function is exact, you have to take the second derivative. When you take that second derivative, you flip this order of operations. So now I'm just going to call this function g, and I'm going to call this function h. If I take the derivative of my above function g with respect to y, and I know it's y because the first time I did it with respect to x. So if I take the derivative, oops, that should say x, derivative of g with respect to y, I'm going to get 4y. I called my function here h. If I take the derivative of this now with respect to x when y is held constant, 4xy, I get 4y. These are equal. Therefore, this is an exact function. Okay. Why do you care about this? Well, exact functions are ones for which the order in which certain changes are calculated don't impact the overall change. I can take the derivative with respect to x and then y, or the derivative with y and then x, and I get the same answer. Mathematically, what you say is that the infinitesimal change of an exact differential is independent of the path between limits, blah, blah, blah. This sounds a lot like state variables, right? It is independent of path. And in fact, that turns out to be exactly true. State variables are described by exact differentials. Path variables are not. right? And that's the important point. State variables are described by exact differentials. Path variables are not. I'm going to give you two other relationships, and I'm not going to go into them. So the first one is called an inverter, right? And I won't try and describe the math, but you can see that the inverter tells you that the partial of z with respect to x is equal to 1 over the inverse. So you can inverse partial derivatives. And the second one is called Euler's chain rule. Right? This is pronounced Euler's. You'll always look like a newbie if you pronounce this Euler, but it's Euler's. And Euler's is written right here. So again, I have some function, which is a function of two variables. It's an exact differential. If you look at these three terms, here's xy, yz, zx. Those are all three permutations. It looks like you would be able to cancel these partial terms. So dy would cancel with dy, dz would cancel with dz, dx would cancel with dx, and you might expect to get 1. But in fact, you will get -1, right? So this is called Euler's chain rule, and it becomes useful for calculating complicated things, or can be useful. I'm going to stop here, and I'll talk a little bit more then about the Maxwell relations in the next video, and I will see you then.